So hello everyone. So this is the second video of the playlist Semiconductor Physics, and here we will discuss about the classification of semiconductor. So we have to classify the semiconductor based on their purity and nature of charge carriers. Purity means like whether any other material is added inside the semiconductor in order to increase their conductivity, or any changes, any external energy we supply. Depending upon that, we have classified the semiconductor into two types. One is intrinsic semiconductor and the other one is extrinsic semiconductor. A typical semiconductor crystal in which silicon atoms are present. So as silicon is a tetravalent atom, so it will make 4 bonds with neighboring 4 silicon atoms. So these silicon atoms basically making bonds with 4 neighboring silicon atoms, like this and this one and this one. So 4 neighboring silicon atoms are making bond with this central silicon atom, and like that, in that way the whole crystal structure is expanded. So here we will basically discuss about the concept of hole. What is a hole basically? So by some means that means if we apply some amount of energy, or by doping, we will discuss about these things later, but by doing these things basically we can eject any electron from the semiconductor crystal to make it conductive. So to make the semiconductor conductive, we can apply some amount of energy, or we can do doping. So by that basically, suppose we apply some amount of energy, then one of the electron from this crystal will move away to the conduction band. So by suppose we apply some amount of temperature, or we increase the temperature basically, then this electron will be move away. So due to, as this electron is moving away from the crystal, so there is a vacancy of electron is created. This is basically a 2 electron bond, but due to the absence of this electron, there is basically a vacancy of electron. This vacancy of electron is called hole. So what is hole? Hole is basically vacancy of electrons. We will now discuss about the first type of semiconductor, that is intrinsic semiconductor. So these are basically pure semiconductors and there is no impurities present. So what do we mean by impurities? Impurities means any external foreign materials is added into the semiconductor crystal. So in this type of semiconductor, no foreign materials basically added. So this is a pure semiconductor. Basically intrinsic semiconductor is a pure semiconductor, and the number of excited electrons and holes are equal. Basically as much as electrons are moving from the valence band to the conduction band, that much amount of holes will also be generated. So number of excited electrons and holes are equal. As we know, semiconductors have negative temperature coefficient of resistivity. So if we increase the temperature, basically the conductivity increases. So if we apply energy, heat energy, basically we increase the temperature, then the basically due to its negative coefficient of resistivity, so due to negative coefficient of resistivity, the resistance goes down and the conductance will increase. So due to increase in the conductivity, it is a very good, it will be a better or good conductive material, so we can use it. Now to the second kind of semiconducting material, we will discuss about a small concept, that is doping. So what is doping? This is a process basically adding foreign impurities in a pure semiconductor. So if we add some foreign impurities in a pure semiconductor, that is called doping. That impurities may basically different materials, like or different atoms. Like if we add we can add boron and aluminum, indium, arsenic, antimony, phosphorus, like that. We can add it different types of materials as per our need. So this is basically called doping. So this process is called doping, and these semiconductors are now called doped semiconductor. After doping, these semiconductors are called doped semiconductor. So dopants are of two types. So what is dopant? Basically the external foreign metal which is added inside the semiconductor crystal, that is called dopant. So dopants are also two types. One is trivalent dopant and another is pentavalent dopant. So trivalent dopants are also called p-type semiconductor. This will generate basically p-type semiconductor, and if we add trivalent dopants in a semiconductor, then that semiconductor will be called p-type semiconductor. If we add pentavalent dopant in a semiconductor, then that type of semiconductor is called n-type semiconductor. So this is basically p-type semiconductor and this is n-type semiconductor. So examples of trivalent dopants are indium, boron, aluminum. Here basically why it is called trivalent, because its valency is 3. So next is pentavalent dopant. Pentavalent dopant is n-type semiconductor, and here impurities are like arsenic, antimony and phosphorus. We will basically discuss about the mechanism of intrinsic semiconductor. So how we can increase the conductivity of an intrinsic semiconductor. So these are basically pure semiconductors where no impurities are added. So in order to increase their conductivity, we have to use thermal excitation. That means if we increase the temperature, then the electrons get excited and out from and move from the valence band to the conduction band. Suppose if we increase the temperature, this electron goes away from the valence band. So here a vacancy will be created. So this vacancy is basically hole. Now this hole is basically vacancy of electron is called hole, and this hole is basically a positive charge because there is no electrons are present. So absence of electron, we can also call it as a positive charge. So hole is basically a positive charge. Now it will attract the neighboring electrons from this crystal. Suppose this electron is attracted, so it will move from this position to this position, and now here vacancy is created. Here is the position where electron is absent. So here basically hole is created. Now this suppose this electron is getting attracted towards this hole, then it will move from this side to this side, and here basically again a hole is generated. Now this electron will move from this position to this position, then basically here also a hole will be created. So in that way electrons are moving and holes are being created, and due to these moving electrons or due to these moving holes, basically current will be flow. So this is the movement of the electron. So this path is the movement of electrons. In this path electron is moving basically. So this is the movement of electron. So what will be the movement of current? Current will be in opposite direction, in this direction. So this is the current flow basically. So this is the direction of current. So in that way the current is flowing in this intrinsic semiconductor. We discuss about the second variety of semiconductor, that is extrinsic semiconductor. So in this semiconductor basically impure materials are added. So semiconductors are doped with impurities of trivalent and pentavalent atoms. So these are basically impure semiconductors which are basically doped with impurities of trivalent and pentavalent atoms, and these types of extrinsic semiconductor basically do not require any external energy supply. That means basically thermal excitation it doesn't require, because impurities are added in order to increase their conductivity. How it will increase, we will discuss it in the later slides. So number of excited electrons and holes are different. Basically in this type of semiconductor, in intrinsic semiconductor the electrons and holes are equal, but in this extrinsic semiconductor number of excited electrons and holes are different. Why? Because because these semiconductors are being doped with different valency of atoms. Like here we are adding trivalent atoms and pentavalent atoms. Due to this the number of excited electrons and holes will be different. So this type of semiconductor is of also two types. Basically extrinsic semiconductor is of two types. One is p-type semiconductor and another one is n-type semiconductor. Discuss about the first variety of extrinsic semiconductor, that is p-type semiconductor. So in this type of semiconductor, p-type impurities are added. What is the p-type impurities? They are basically the trivalent atoms. The trivalent atoms are boron, aluminum, like that. So here basically in this p-type semiconductor, p stands for positive charge. Why positive charge? Because due to addition of trivalent impurities, holes are created. So in this type of semiconductor, holes are generated. That is why it is called p-type semiconductor, and it is also called as acceptor, because due to creation of the hole, basically it will attract electron. So this is basically acceptor. This p-type semiconductor is also called acceptor. And then here holes are majority charge carrier as its density is maximum. Acceptor and here another impurity or energy level is there just above the valence band, that is the acceptor impurity level. So acceptor impurity level, why it is created? Due to generation of the hole. This hole basically attract the electron. Due to attraction of the electron, basically it moves from one side to the another, move from one position to the another. That's why the conductivity of the semiconductor basically increases. That is why it can increase the conductivity. So acceptor impurity level is just above the valence band, because this energy level is easily created due to addition of the trivalent impurity. Energy band diagram of a p-type semiconductor. So what happens in a p-type semiconductor? Basically there are three energy levels. One is valence band, another one is acceptor energy band, and other one is the conduction band. So why this acceptor energy band is created? When we are making the p-type semiconducting crystal, we will discuss it in the next slide. Basically when we will basically discuss about this crystal, so there is trivalent impurities are added. Due to addition of these trivalent impurities, the silicon or the semiconducting material will only make the bond with 3 electrons of the trivalent impurity, but one extra electron is still left to make a bond. So this extra electron is basically unpaired. Due to this unpair, basically one electron, we can also say that one electron is less, or there is a deficiency of electron. So due to this deficiency of electron, basically hole is created. So this hole can easily attract the neighboring electron from the semiconducting crystal. That is why this acceptor energy band is just above the valence band and it is lower than the conduction band. So electrons can move from the valence band to the acceptor energy band, so in order to increase the conductivity of the semiconductor crystal. So here you can see this is basically a typical structure of p-type semiconducting crystal. So silicon atoms are there, and in the center there is a boron atom present. This boron is a trivalent impurity, or that is why it is creating a p-type semiconductor. So the 3 electrons of the boron are making bond with the neighboring 3 silicon atoms, but 1 electron is deficient in boron. So that is why this silicon atom is being unpaired. So due to this deficiency of electron, basically hole is created. So this is basically making a hole. So this hole will attract the electron. So now the electron will move towards this hole. So this electron is basically moving towards this hole, and here a hole is, another hole is created. So due to this hole, basically another electron will be attracted. So now it will occupy by another electron, and here another hole is created, and in that way the electrons are keep on moving and holes are being created like that way, like in this way. So this is basically increasing the conductivity of the semiconducting material. So this p-type of semiconductor, why we called it as a p-type semiconductor? Because p stands for positive charge. And why positive charge? Because holes are being created in this p-type semiconductor, which is basically facilitate the conductance of the material. The second variety of extrinsic semiconductor is called N-type semiconductor. So in this type of semiconductor, basically N-type impurities are added. N-type impurities are the pentavalent atoms which are being doped with the semiconductor. So here N stands for negative charge. Due to addition of these pentavalent impurities, one extra electron is basically present. That is why it is called donor. So electrons are here majority charge carriers as their density is maximum, because maximum electrons are present, and basically electrons are contributing in the conductance, and the donor impurity level just lie below the conduction band. So this conduction band, in the below the conduction band, basically impurity level is light. So from this conduction band, electron is moving towards the conduction, the electron from the donor band basically moving towards the conduction band. That is why ease of electron flows and the conductivity of the material basically increases. Basically the energy band diagram of the N-type semiconductor. So here are also three bands, that is valence band, conduction band, and the extra band is the donor energy band. Why this donor energy band is created? This is created because of the extra electron present in the semiconducting crystal. So in this N-type semiconductor, basically pentavalent impurities are added with a tetravalent semiconductor. So this pentavalent atom will basically make 4 bonds with the neighboring silicon atom, but one extra electron is still left, which is basically unoccupied. So this extra electron is basically free mobile electron, so it can easily move from the donor energy band to the conduction band. So here the donor energy band just lie below the conduction band, because the electron is basically free or mobile, so its energy will be more than these valence electrons. So that is why the donor energy band just lie below the conduction band. You can see basically this is a N-type semiconducting crystal. So in this N-type semiconductor, basically in the central atom N-type impurity is present, that is antimony, and it is making 4 bonds with the 4 neighboring silicon atoms. But as it is a pentavalent atom, one extra electron is also there, which is basically unoccupied. So this extra electron is free and mobile, so it can easily move from the donor band to the conduction band. So this electron is basically moving from the donor energy band to the conduction band. That is why basically here a hole is created. Now this hole is occupied by another electron, and in that way the conductivity of the N-type semiconductor occurs.